My name's George Bugh. It's May 6th, I think, 2016. Happen to be at home alone with nothing else better to do, so I thought I'd just make a quick video to explain where gravity comes from. It's probably not a coincidence if you see a lot of correlations between what I'm about to tell you and what you may have heard from Bob Lazar many years ago. I did a lot of research maybe starting 15-20 years ago, and published a book and stuff like that, and then started watching YouTube videos and started coming across Bob Lazar's videos of his work and started seeing a lot of correlation. And so I think there's a lot of truth in the things he's saying, but I see some things that just look like they're not really exactly right. So I'm guessing it was disinformation, maybe not purposely on his part, possibly just people giving him information for his part of his job. We're not giving him the completely accurate information, just as a way of keeping as much stuff compartmentalized as possible. Anyway, here we go. It's really simple. You start off with an atom. We'll just do a helium atom here to keep it simple. You have neutrons, protons, and you have a couple of electrons. And they're moving around in their orbitals, or in their one shared orbital, with one of them with upspin and the other with downspin. Per Pauli's exclusion principle, they naturally develop upspin, downspin for each electron pair. And this is true no matter what kind of element you're talking about. How many ever electrons you have and however many orbitals, their orbital motions are not like orbiting planets. If you're a chemist, you know all about all that stuff, the different shapes, the different orbitals. Regardless, they pair up, upspin, downspin. In reality, what they call upspin, downspin are axes of precession. And there's actually, the actual spin axis is at an angle, and it precesses around, kind of like a gyroscope. And both of them do this. And classically, this is why they do it. Has to do with relative motion and magnetism. Anytime you have relative motion, it causes a magnetic field, a relative motion between electric charges. It causes magnetic field to be manifest from the point of view of one charge versus the other. So from an outside point of view, we don't see it, but for an electron whizzing around in various motions, classically speaking, since ultimately, although it's not accepted right now, the classical way of describing things actually does work if it's done correctly. So I'll just describe this classically. If you have an electron whizzing around and you have protons, let me take a break, get a better marker. You have protons in the nucleus. For helium atom, you've got two of them. So, whenever an electron's moving relative to this, then from the electron's point of view, there's a magnetic field. If the electrons moving this way. The protons, from its point of view, appear to be having a magnetic field due to the relative motion, and this is totally separate from the magnetic field that is already characteristic of a proton due to its own spin properties. I'm not talking about that magnetic field. I'm talking about the magnetic field that generates only from the electron's point of view due to the relative motion between the electron and the protons. The protons also see a magnetic field coming from the electron due to its motion from their point of view. However, it doesn't have much effect on these because their mass is so much more. The primary effect it's going to have is on the electron. So, as this moves around from its point of view, it sees a magnetic field, and the magnetic field has torque that it applies to the spin axis, which is not this precession axis. Quantum physicists love to point to the precession axis and say that's your spin up or spin down axis, and that is not true. That is your precession axis. Your spin axis is going to be precessing around, and the reason it does has to do with vector equations. I'm not going to go into the math. You can go online and research it, gyroscope and all that kind of stuff. But what happens is, if you have something that's spinning and you apply torque on it to try to twist it around, either gravity pulling on a top or a magnetic field pulling on the magnetic dipole through the spin axis, if the electron's spinning, and you have a magnetic field. Let me do it this way. You have a magnetic field, and it's applying torque to that magnetic dipole through the spin axis. It does not just turn straight down and line up with this magnetic field. Instead, the torque applied to it causes it to have gyroscopic motion around that direction. So, the magnetic field wobbling around in this direction is going to be radiating electromagnetic waves. So, because, what's the best way to say this? First, north is pointing more that way, and then as this comes around, south is pointing more that direction. So even if the axis of precession stays relatively the same, this is going back and forth radiating electromagnetic waves. And if you have around the nucleus of an atom multiple electrons, we'll just show one pair. Let's say you have this electron pair, this one with up spin, this one with down spin. That's the precession axes of each. They really also have the real spin axis that's wobbling around, and this one's wobbling around. And quantum physicists will tell you that we can just ignore that. These are compensated spins. You don't see it outside of the atom. Only when you have an unpaired electron will you see and be able to interface with that RF signal that's radiating from that gyroscopic motion. And that's what the field of electron paramagnetic resonance, electron spin resonance is all about. And when you go get an MRI, that's what nuclear magnetic resonance is. They do the same kind of thing for the protons. If you have an unpaired proton, you can access and stimulate that frequency and get a signal back from it if you're at the resonant frequency that it likes to wobble at already. So when you have paired electrons, supposedly, well, they all cancel out. You don't even see that. Well, that doesn't mean it's not there. You still have electromagnetic waves coming from both the up and down spin paired electrons in various orbitals around all atoms. The reason you don't see it is they tend to synchronize. And that's finally the heart of what this video is about. I'm about to tell you right now. It's all about how they tend to synchronize. So, what's the best way to say this? I'm going to turn this whole thing on its side. We'll call this up spin and down spin for pair of electrons, and these are in orbitals in the same orbital around an atom. So this is the actual spin axis. This is the actual spin axis, both of them wobbling around. So what happens is they tend to, they will precess at the same frequency, and the phases are such that they are similar to two bar magnets. I'm talking about only that vector of its magnetization vector that is going to be going around this way. I'm not talking about the precession axis. There's another portion of the magnetization vector in that direction also. And that's not what we're talking about right now. We're talking about only the portion of the magnetic field that's going around. So, imagine all that sideways for two electrons. That magnet, let me show it like this. Here's your up spin, and here's the real spin axis. That's the axis of precession. There's down spin, and its real spin axis, and it's going around like that. And this one's precession around like that also. Okay, so we're going to take this whole thing and turn it this way. And that's what this and this are. They are the vector portion of this and the vector portion of that are both facing that direction. So now that's the up direction. So they precess at the same frequency. So I'm going to draw them overlapped. Once per revolution, they're both pointing up. As they continue, another marker's giving out. Let me get another marker. I'm making all these mistakes so people who think they know it all already will get tired and give me bad feedback and stop watching. The rest of you who really want to learn something, you can keep watching. Okay, so they're both pointing up, they're both precessing at the same frequency. So once per 360 degree turn, they're up. 180 degrees later, they're both pointing down. And in between, they're going like this. One's going one way and one's going the other. Everything outside of them, this north, that magnetic north, rotating this way. This one's rotating that way. This one's rotating this way. So everything outside of here, if you remember, if you have a magnetic field pointing one way and it's moving another way, then it applies an EMF on charges the third axis, the third direction. So this is pointing down and going this way. It'll push charge in and out of the blackboard, and this one will push charge in and out of the blackboard the other way. And so it tends to make an EMF that's trying to make a current loop going around this way for electric current. And that's the maximum amount of EMF is when they're in this direction. As they spin on around and are both pointing down, you have a minimum amount of EMF. However, you have a maximum amount of north. That north is rotated down, is pointing down now. So it's like that. So what happens is, when both are pointing up, you have a maximum magnetic field, and the electric fields, the EMFs are canceling out. The same amount of force trying to push one way gets canceled out by the EMF force trying to push it the other way. As they rotate in opposite directions around to this angle, the EMFs are such that they're trying to make a maximum amount of current flow looping around one way or looping around the other way. As they rotate past here and they flip around the other way, coming back up north again, they're going to be trying to give maximum EMF the other direction. So what happens is, twice per cycle you'll get a maximum EMF trying to make a current loop in this direction, and twice per revolution you have a maximum north pointing up, and then a maximum north or up, and then a maximum north pointing down. These signals, although we don't see them because we don't usually have equipment designed to pick up AC magnetism with the electric field portion canceled out, we don't have equipment that usually designed to pick that up, so we don't see it, and it pervades even the atoms of any test equipment you might try to use, so it's not an easy thing to see. So nevertheless, that alternating magnetic field is radiating out from all atoms, and the frequency is dependent on how they move around in their respective orbitals, how many positive charges are in the nuclei, causing a magnetic field from their point of view, which affects their Lamar frequency. That's that frequency of precession. The bottom line is, if you have an accumulation of mass, like in the Earth, all those alternating magnetic fields interact between similar orbitals of all the electrons within that mass, and it does so in such a way that those alternating magnetic fields are radiating out in this direction, in all directions, like that. Going north, south, north, south, north, south at extremely high frequencies. And if you remember, I said twice per revolution, precessional revolution, these will be trying to create an EMF to create current loops in this direction. So going in and out of the board, and if you sum that all together across the surface of a sphere, they're all neutral. You don't see it. You might see some noise that could be interpreted as background noise, but you don't really see huge current loops going through the Earth, because the vector summation of all those synchronized, they're all synchronized, but small loops all over, all going the same way at the same time around the Earth. When you do a summation of that over a spherical area, it all tends to neutralize. So the big effect that really matters is twice per precessional revolution, you get all these magnetic waves that are coming out of matter, whether it's Earth or anywhere. So, the conjecture that I'm making is that what Bob Lazar calls gravity waves A and B really do exist. It's not the same thing as when you have like a star that collapses in on itself or goes supernova or whatever. So you have suddenly a huge change in the position of mass, and the gravity wave created by that propagates out in the space. That's a gravity wave describing kind of a step change in how much gravity from a certain location, and that ripples out. I'm not talking about that kind of gravity wave. I'm talking about the actual AC magnetic flipping polarization directions that comes from all atoms, electrons from around all atoms that radiate out, and they synchronize with each other. These push and pull on similar paired electrons in all other atoms, and so the tendency is for them all to become synchronized with each other and their magnetic vectors to sum together. And it gets more complicated in that there's not perfect harmony, perfect phase synchronization. There's actually spin waves. It's kind of like thermal noise within these sets of magnetic waves that all tend to sum together for large bodies of matter, or any mass. You know, they sum together and create the effect we know as gravity. And yes, gravity is a warp in space-time, and the only difference really is you can think of electric force as a warp in which it's a proportional amount of warp in both time and space, whereas due to the way they interact with each other, it's disproportional warp for gravity, and so then it manifests itself. I mean, it's still there for an electron, but we just see it as an electric force pulling on other electric charges. But due to the way they interact with each other, it's disproportionate in time versus space, and I know that all sounds wacky, but it's really, there's hardly any difference at all. It really is just a warp in space-time that causes gravity, and there's a similar kind of a warp that's causing other forces, like primarily the electric force is what I'm trying to say. So they're very extremely similar. Okay, so if by some miracle you grasp all of that, then there's a second, much higher frequency, similar precession if you have protons and neutrons in a nucleus. The helium nucleus, 2 protons and 2 neutrons. So what we are told all our life is the nuclear strong force holding them together. Just imagine the particles, the quarks that make these up, are precessing also and interacting with each other. If I remember right, quantum physicists and quantum electrodynamics, they call them gluons rather than photons. Gluons is electromagnetic, or gluons is not, they don't call it electromagnetic, but they call it the force carrier that of the nuclear strong force that binds these together. But you really could just think of it as extremely high frequency electromagnetic waves, and that would be more accurate. It sounded crazy when Bob Lazar said that, but he's actually right. It's just they precess at much higher frequency, much more short or close range interaction. We don't see it from outside the atom because it's all compensated for. If you have an odd number of protons, there's a signal there probably, but it's such high frequency, maybe in the terahertz range, maybe up in the range of gamma rays. because it's a much higher frequency precession, and the signals they exchange with each other, binding them together, and also a portion of it radiated out into space, and all similar protons and neutrons will synchronize their motions due to the receiving the signals. So basically it's kind of like the same kind of interaction that's going on with paired electrons, but a much higher frequency for the motions of quarks within the nuclei. And that is what Ernst Mach alluded to as there's some kind of interaction going on between matter and the whole universe, otherwise you couldn't have inertia. And just do a quick review of that, what Ernst Mach is talking about. If you imagine a man in a space suit and he's holding a couple of buckets. That doesn't look like a bucket. Holding a couple of buckets, and the buckets, there's your handle, there's your bucket, here's your handle, there's your bucket. And I won't say he's got water in them in outer space because it would all evaporate. Let's say he's got some sand in his bucket and sand in this bucket. And if the universe spins around him in this direction, somehow the universe spinning around him causes the buckets to be pulled out away from him. If you're watching him and he's perfectly still, then that really means, from your point of view, the universe is spinning around you also. So relatively speaking, another way to say the same thing, if you and the guy you're observing are both, if the universe is not moving, but you're watching this guy and from your point of view, he's spinning, then there's a force pushing his buckets. I'm a terrible bucket drawer. Here's just buckets of sand. There's a force pushing his buckets out if he appears to be spinning from yours and the universe's point of view. But if you say the universe is spinning and he's still, and you are still or not, either way you're observing him, if he appears to be still and the universe spinning, that force is pulling him out. But if he's still and he's still relative to the universe, there's no force pulling the buckets out. So Ernst Mach making that observation where you say it's out in space or on Earth, wherever you do the experiment, you know, you can do it, whether you're in a gravitational field, he's standing on Earth doing this experiment with weights. If he's spinning, there's a force doing this. It's no dependence on the Earth being here or not. It's going to happen whether he's on Earth or in outer space. If he's spinning relative to the universe, something makes a force pushing him out, even though you could be, along with him, in relative stillness, not moving at all. It could be the universe is spinning, and the fact that that's happening will cause the force to go out. So Ernst Mach saying, well, that's impossible unless there's some kind of interaction between him and the universe. Somehow the universe has to know he's moving, or he has to know the universe is moving in order for that force to get generated. So my conjecture is that ultra high frequency precessional waves, precessional motion generated waves coming from atomic nuclei. George Bugh again here. This is a follow-up to the video I've already made about where gravity comes from. I thinking about everything I said and anticipating questions people might have. And so this is a follow-up video to cover that. One of the most obvious ones, I don't even have it written out here on the board, but that is, how can I assert that we can look at the classical processes going on with electrons and say they actually work, when in the past scientists believe they've shown that you have to resort to quantum mechanics or quantum electrodynamics to accurately describe the characteristics of an electron. One of the primary concerns, for example, is if electrons do radiate electromagnetic energy from their spin and precession motions, as they should per classical electrodynamics, why don't they radiate away all of their energy and just evaporate? So my contention is not only some local group of electrons around whatever atoms you're considering, not only are they radiating away energy, but all electrons everywhere and all atoms in the universe are also radiating away energy. And so it propagates through space and time and ends up applying electromagnetic forces to other electrons everywhere, and those forces naturally pull them into synchronization such that energy that's lost from radiating out from precessional and spin motion is also ends up being another electron's energy received that maintains its energy level. So all electrons everywhere both radiate and receive electromagnetic energy. It's created a huge sea of standing waves among all matter. We don't see it because it permeates any test equipment we would usually try to use to see that. There are ways to see it, but that's not something people have considered in the past, so they haven't researched that area. So if we move forward with the assumption that we can use the classical equations based on the correct assumptions of electrons, then we can make it all work. And so, for example, another assumption that in the past has been wrong is that, well, this can't work. We can't consider the spin characteristics classically because it would require the sphere of the electron to be way too large. And so here again, we're making a wrong assumption that the electron is a solid object that's coated or filled with this substance we call charge. That's a wrong assumption, and a better assumption would be to think of it as a small vortex of electromagnetic energy. The same characteristics of space itself that allow electromagnetic waves to propagate, specifically coefficient of permeability and, or I should say inductive permeability, and the coefficient of capacitive permittivity, they work together to establish what you might consider the elasticity or springiness or warpiness of space itself. And that's what allows electromagnetic waves to propagate, and that's those specific values of those coefficients are what actually set what the speed of light is. So those same characteristics of space also allow for vortex motion, although this has not been described accurately that way recently. 100 years ago or so, Helmholtz and others have shown how you can describe electrons and other charged particles as the vortex motion of energy. And that requires us to consider the possibility of something we call an ether, and people have mistakenly assumed that we've disproven the existence of ether, or we've shown we don't need it in the equations, so we can just stop considering it, and that's a mistake. It's kind of like using Occam's razor, intending to do the circumcision down to the bare truth and accidentally castrating the truth so it's gone. You should consider the possibility that there is actually an ether. Famous experiments that supposedly showed us that it did not exist or that we don't need to consider it actually never proved at all that it does not exist. They just proved that the way we tried to measure the assumptions we made about what were the correct characteristics of ether were wrong. And so ether, the existence of an ether has never been disproven. And if you still have heartburn over that whole concept of there being an ether, then the easiest thing to do is just substitute that with definition of ether as those characteristics of space that give space a specific value of coefficient of permittivity and coefficient of permeability. And whatever that stuff is, whether you want to call it an ether or whatever, that basic characteristic of space itself allows the classical explanation of electromagnetic interactions to work if you use the correct assumptions in your research. And so if you followed what I said in the first video, I anticipate you get to the point in the video where you say, well, how can I say just because paired electrons radiate away alternating magnetic fields, how can I jump forward and say, well, they're synchronized and they create sets of magnetic waves alternating back and forth, radiating out from accumulations of matter or mass. So this video, I wanted to talk about that some more. I don't have it all rehearsed what I'm going to say, so we're just going to ad-lib this and see how it goes. So just to back up a little bit and discuss how any and all matter interacts with other matter. In thermodynamics, we're well aware that the concept of entropy, where randomness tends to increase in general. And specifically, if you have an accumulation of particles in random rectilinear motion, or specifically charged particles in random rectilinear motions, they interact with each other to become more random in general. And so we call that Brownian motion usually. And my contention is it's a big mistake to take those concepts that were originally developed from observing and creating equations to represent thermodynamics of systems that are primarily dominated by rectilinear motions. And it's a mistake to take that and then try to apply it to systems that primarily involve random rotational motions. If you do some thought experiments, you should be able to see, let me go ahead and erase all of this. If you've absorbed what I got here, you can come back and look at it in the video. If you have not. If you have random rotational motions of charged particles with the attribute of spin and magnetic dipoles through their spin axis, we can consider that just to simplify it, in a two-dimensional array to begin with. If you have accumulation of bar magnets, probably a bad marker again. If you have an accumulation of bar magnets in random orientations, and we're just considering it in flat plane to begin with, just to simplify things, but The same concept can be extended to 3 dimensions. If you have an accumulation of magnetic dipoles pointing all kinds of random positions, it can be a huge number, billions and trillions of these. Imagine them all in a random orientations. This can just go on expanding outward. If you start at T0 and let this array of random orientations go, just to freely interact with each other's magnetic dipoles as they choose, I'm hoping your visualization skills are good enough that you can see, obviously, they're going to move to a state of greater order. Not less, not more randomness. So the whole thing will either become magnetized, more like this, or obviously, as occurs naturally within solid state physics, within solid magnetic materials, you're well aware of, well, they also become organized like this. So the north and south tend to interact with each other. So they try to reach a state of lowest potential energy level, usually like this. And depending on what kind of material you're working with, how long they stay magnetized in one way, how soon their crystalline structure flips back and neutralizes itself like this, or expand your visualization to try to see how that's going to happen in a liquid or a gas also. Natural tendency is, regardless of the order, it is a more ordered state than the initial randomness. Regardless of whether they try to all do like that, or they extend some and have a lot of norths together before they turn back the other way. Hopefully the bottom line is you can see, obviously, any of those options are a more ordered state than the initial randomness. So now we consider, again, you have an accumulation of atoms, and you have paired electrons in various orbitals around the various atoms, and each paired electron set per Pauli's exclusion principle, which is again a demonstration of it trying to go immediately to the more ordered state with a spin up and a spin down, which I'm going to show sideways now, but you get the idea that there are opposite directions. They're all going to be like that, all of your electron pairs moving around in their various orbitals of various shapes. So hopefully you will concede that this is common knowledge. I don't need to expand on this point further. So then we consider, per classical electronics, it's more appropriate to refer to this and this as your axis, or axes for plural, of precession. And in fact, your real spin axes will be at some angle and it'll be precessing around, this one will be precessing around the axis of precession. So then the next point or question or topic to talk about is how can I assert that these let me first say these axes are going to be spinning around more in and out of the board, of the whiteboard here, one way or the other, in opposite directions, because one's spinning one direction, one's spinning the other with their axes of precessions in opposite directions. So then the question is, how can I assert that those motions will become synchronized with all other paired electrons? So first, hopefully we'll concede that two paired electrons in the same orbital will precess at the same frequency, and that's due to the fact that the thing causing them to precess in the first place is of equal quantity for both of them. The magnetic field that appears to exist coming from the protons in the nucleus, it's the same strength for both of them. So they'll precess at the same frequency. So then, if you can fix that in your mind and you've got good abstract visualization skills, you'll be able to consider now this and this to be, this for example is an electron with up spin, and this is your real spin axis. Okay, from here on out, try to remember the total magnetic field is changing all the time, and so instantaneously at this snapshot in time it's pointing down. So that means there's a vector portion of it that's facing the precession axis direction, and another vector portion of it that's facing down and that continuously precesses around. So from here on out, when I'm drawing these arrows, I'm describing and discussing this portion, the portion that's continuously changing at the precession frequency. Okay, so fix that in your head. These arrows represent, I guess, to make it more clear, I should point down, since I got this one down at this snapshot in time. So that's represented by these for electron pair. So if you can accept the fact that they're precessing at the same frequency, one's going to precess out of the board and the other's going to precess into the board, and they're going to come around, and at the precession frequency they're going to cross at the top and both be pointing up. If we call up 0 degrees, then down would be 180 degrees. And so they also pass through 90 and 270 degrees, and then on the other way around they pass through 270 and 90 degrees before they come back around to 0 degrees again. So if you can fix that in your mind with your abstract visualization skills, then the question I'm trying, or the topic I'm trying to discuss is, well, if that's how they are for one set of paired electrons, how can I assert that all these other electron pairs and all these other orbitals around an atom or a whole bunch of atoms, how can I say that, well, every one of them is going to be up 0 degrees between all of them, those precessing pairs, at the same time? They may or may not for orbitals where the electron pairs actually precess at a different frequency from one orbital versus another. That's going to be dependent on the strength of the magnetic field they perceive coming from the protons in the nucleus. So let's just isolate one particular orbital to begin with, and I'm not a physics or chemistry expert, I'm not an orbital expert, but let's just say, let's talk about which is the most common orbital of all atoms. That's going to have the most precession pairs of electrons precessing. Of all atoms, like for example for the Earth, there's going to be a particular orbital that is most common with the most precession electrons in it. So let's talk about whatever that frequency is that they precess in, as determined by classical electrodynamics. Excuse my poor ability to talk. So then, whatever that frequency is, what is it that's going to make all of these precessing pairs move into similar phase? Not only, we know already that with the same magnetic field strength that they perceive, they're already all going to precess at the same frequency. So then the only thing to discuss, to consider next is, well, what makes them all the same phase also? So, if you consider, let me erase all this, fix all that thought, all that image I'm trying to paint in your mind, fix it in your mind, and then let's move on from there. Let's consider, okay, one particular electron pair at T0, at that point in time, we'll say they're both pointing per however we arbitrarily decide to set our coordinate system for rotational motion. We'll say at T0, this particular electron pair are both pointing at 0 degrees for straight up. So you got all these other electrons and so ever many atoms in the area, and those precessional pairs are precessing at the same frequency. So what's going to make this one be up and all these others, however, billions, trillions of trillions pairs that you got, what's going to make all of them all be up at the same time? So one way to try to visualize it is just consider them all to be bar magnets, since that's what you got. Pairs of bar magnets. And I'm telling you, at a point in time, they're both north-north and south-south. And so if your visualization skills are poor, you're going to say right away, well, no, that's not going to happen. One of them or both of them are going to immediately flip. So they're like this, because that's a lower energy state. Try to back up in your mind and remember that Pauli exclusion principle already set them up and down spin, and we're still talking about their axes of precession. That precessional motion is not going to become stationary. They're still precessing, so they can only remain in this position at a particular instant in time, and they will continue to move past each other and flip on over. So it is true that at a particular point in time they're going to be like that, and if they are, then 90 degrees motion later, it's going to come around where you got a south-south pointed at you, or they're going to move around to where you have a north-north pointed at you. But nevertheless, they're going to keep doing this kind of a scissor motion. If you you can understand what I mean. This is going to be their common axes flipping around in a scissor motion. And I'm not trying to imply that they're lined up that way in each orbital for each pair of electrons. Regardless, if you have a nucleus here with a lot more protons than this and tons of precessing paired electrons in various orbitals around them, even if one electron's here and the other's here, or one's here and one's here, if you zoom way out from the object, it's still as if they're practically next to each other. So no matter how you consider them next to each other or far apart from each other in their orbital motions, from an outside observer's point of view, they're still practically next to each other as far as considering this precessional motion goes. So we can, hopefully you can understand why it's reasonable to just say we can represent them like this and moving kind of in a scissor motion. So what's going to happen is, outside of this pair of electrons, it's not radiating any, at this point in time, it's not radiating any magnetic fields external to itself, because these opposite poles compensate for each other, and we're still talking about the instantaneous precessional angle and not the up-down spin axes of precession. At this point in time, they're compensated for each other, and because they're moving one way and one the other, they're creating an EMF, electromotive force, or voltage essentially. They're creating a force that any electric charge in the area would be pushed in a motion that is both at right angles to their rotational motion and at right angles to the direction their magnetic field is pointing. So if it's sweeping this way and the magnetic field's going this way, then it's going to be trying to push electric charges in this direction. And the same on the opposite side of the axis, where the south and the north are crisscrossing each other from opposite directions. There also it will feel electromagnetic or electromotive force pushing the other way. So that's why in the previous video I said you're going to have current loops, small current loops, induced one way or the other. And that's going to happen twice per precessional rotation. So at two other points, 90 degrees plus or minus this position, they're going to end up both north facing a particular direction and both south pointing a particular direction. And the same for all other, if this dot represents two of these and this dot, this dot, this dot, if all of these are accumulation of electron pairs in one atom, and now we zoom out further and that total atom's worth of electron pairs are represented by one dot. You got all these dots that represent different atoms, and you take all that, you zoom out even further, that accumulation of atoms equals one molecule, and that represents an even greater number of precessional pairs, and that molecule's accumulated with a bunch more to represent a body of matter, of mass. You can keep zooming out and understand we're still talking about all the electron pairs of all those atoms, and in particular those electron pairs that are in the most common orbital for electron pairs to exist in for most matter. They're all going to be moving like this. I've had several days of interruptions and trying to get back to where I was, so made some notes, and I'll go through and talk about these notes as a way of covering where I left off before. Hopefully I won't miss too much. So first thing I have here is I was talking briefly before about the thermodynamics of rectilinear motions versus the thermodynamics of rotational motions. Just to give you a better example of the difference, let's consider a box, isolated box, thermally isolated from everything else in the universe, and inside the box you have some balls, and they initially start off in a very ordered state with all these moving this way, the same velocity, all these moving this way at the same velocity. However, when they collide with each other, they do not hit each other dead center. There's going to be some misalignment, and so hopefully you'll visualize and understand that very quickly they'll start bouncing in odd directions and interacting with each other to end up in a very disordered state. Assuming no energy is lost to the walls or to friction, they would just keep bouncing around, and the total state of order would continually decrease. Entropy would increase, meaning the amount of disorder in the system would increase. They continually move to a more disordered state. So now, I talked about this before, just review. If instead you have random rotational motions, let's assume this time we have a set of magnetic dipoles that are pinned in position, because we're not trying to consider rectilinear motion this time, we're just trying to consider rotational interactions. They start off at random positions. Hopefully you can visualize in your mind at T0, if you let them all go to rotate to any position they want in this two-dimensional plane, then very quickly they'll all move to a more ordered state. So I talked about that before in magnetic materials. If it's like a hard magnet, they move to a more ordered state, and the exchange interaction, which is really electromagnetic signals exchanged by the precessional motions of the uncompensated electrons that are the source of the magnetism of the magnet. They keep them propped up in that more ordered state. They keep them in a state of hard magnetism. Or if you have a soft magnetic material, meaning that it's very easy for some external magnetic force to reorient them all to a new direction. Hopefully you see how whichever magnetic orientation they move to, that's an ordered state. You take away some external magnetic field and they'll move back to some disordered state, random magnetic state for all the magnetic dipoles within that soft magnetic material. So hopefully you can visualize what I'm talking about there. So now take that same idea of rotational motions, moving to a more ordered state, and extend it to continuously moving magnetic dipoles. So let's take an example of 3 electrons. They all have upspin.
and their axis of precession are going like this, and they're within a magnetic field that causes them, there's some external magnetic field that they're sitting in, homogeneous magnetic field, let's say, although I'm not drawing it very well at all. So anyway, it makes them precess. So if this one and this one are in phase, they're going to interact with the one in the middle and eventually change its phase, so they will all be in phase. Their natural tendency is to all move to a more ordered phase. And if you expand that out and look at a whole lot of electron spins, they never have perfect order. There'll be spin waves among them where it'll ripple through in different directions, but the overall tendency is to try to be in phase, even though there's some amount of spin waves from whatever amount of phase differences they have between them. And that same idea you can extend from 2 dimensions into a 3-dimension sample as well. So if you're a physicist and you know all about magnetic materials already, you know about all this kind of stuff. So the point that I want to get to is, now assume you have paired electrons with upspin and downspin. Well, first off, they're not going to just, by pure luck, have their upspin and downspin all facing the same direction relative to each other. But they will radiate sets of magnetic waves, like I talked about in the previous video, and those will cause them to interact with each other. I'm going to talk about that more in a few minutes. Let me get on to the next set of notes here, since it's kind of necessary to understand all of this that I'm going to talk about first before I get back to that. One other thing I wanted to talk about, just because I know there's a lot of people just looking for anything to be critical about without really trying to understand what I'm going to say. So just to address something the critics may say, you remember before I had these diagrams of like the Earth, for example, and I contended that it would radiate waves of toggling magnetic fields, where they'd radiate out with the magnetic field direction swapping back and forth continuously. And I had a diagram kind of like this. And just imagine this continuing on out, representing flipping magnetic fields radiating out from the Earth. So people who don't stop and think very much are going to say, well, I'm an idiot because everyone knows magnetic lines of magnetic flux or make closed loops. You don't just have lines that stop like that. Well, of course that's true. Instead of assuming stupidity on my part, try to understand what I'm trying to say. So you may also be familiar with a diagram that looks like this. If you studied very much about electromagnetic signals at all, you will have seen a diagram like this. And this is an example of a transverse hopefully this won't run off the screen, electromagnetic mode. So this represents electric and magnetic field intensity. I'm not going to draw the whole thing. Hopefully I'm drawing enough that you'll remember from your textbooks. This is a transverse electromagnetic wave symbolic diagram. And if this is your E field strength, this is your magnetic field strength. And they swap back and forth as the wave travels out at the speed of light. And guess what? Look at that, man. The magnetic field lines, they just stop. They're not closed loop. So if you have the ability in your mind to understand that this represents the signal radiating out, it does not try to indicate that magnetic field lines are not a closed loop. It's just showing you how the wave travels out. And in actual real world, if you have like a dipole antenna and you're looking down on the top of it, and your electric field's oscillating this way and this way, this way, and this way, it's radiating out transverse electromagnetic wave. And out here in space somewhere, your E field will be going this way, in and out as it radiates out, and your magnetic fields will be at right angles to that, and they'll make... Am I drawing that right? I'm not drawing that right. Let me draw your dipole this way. If you have your electric field going this way and then this way through that antenna, it's going to radiate out a signal where your electric field is going this way, it's this way. Sorry, I'm doing such a sloppy job of drawing it, but hopefully you'll get the point. And the magnetic field would go going this way and that way. And I don't know the right way to draw it. You have to go online. If you go online on the internet, you can see diagrams exactly how that kind of a convoluted magnetic field does loop back around and connect and make closed loops. So the point I'm trying to make is, if you draw a diagram like this, in this one case, the magnetic field's going in and out of the board, and you see lines that don't go on for infinity or don't make closed loops, that doesn't mean it's really that way. We're just trying to make a symbolic diagram of how the signal radiates out. So please extend me the same courtesy when I make diagrams of flipping magnetic fields coming out of the Earth. I'm not trying to indicate that the magnetic fields are no longer making closed loops. If you have a pair of electrons with upspin and downspin, and then you have the real spin axis precessing around, then if you look at the vector portion of the magnetic field that's going around this way, you're going to have like it'll be equivalent to two bar magnets one rotating into the board and the other rotating out of the board. And they'll be doing like this, a scissor motion coming around. So just like I discussed in the previous video, these will have magnetic fields. You have both norths up at this instant in time. You know, they're going to have magnetic fields like that. So if you want to see it with a computer animation, you just make 2 bar magnets with magnetic fields, and then you do them in a scissor motion, and just slowly cycle through 360 degrees rotation for each of them going opposite directions, and see how their magnetic field lines change as they go on around. When this gets to a position where this is south and this is north, then these won't go like that anymore. They're going to be going, these field lines going over into this one, and these field lines going between these 2 ends. And then that's going to change as they keep rotating around. And I don't know how to draw it as well as you could probably just see it by doing a computer animation. If you're an expert on how to use software to do all that kind of stuff, I don't have the equipment to do that. So that's what I'm talking about when I say they will form closed loops. But the point is, nevertheless, when they're in those 2 positions where they're either both north facing whatever direction you want to consider up, or both south facing the direction you want to consider up, then magnetic field strength wise, just like a transverse electromagnetic wave diagram shows you the strength getting more or less as it radiates out into space, these will have their magnetic field strength getting more or less in the direction that they radiate out, even at the same time that they're always making closed loops. Even if you have to warp space and time to make that happen, they're always going to make closed loops. I mean, if that's the rule we set, then that's the way it's got to be. If you want to get into making a simulation, an animation of this kind of thing, one thing you have to remember that people often forget is that when we talk about a magnetic field, a source of a magnetic field, like let's say we have a bar magnet, the magnetic field's coming this way. Let's say we're rotating that this direction this time, just to make it easier to visualize. We have an axis here and we're rotating that magnet. And let's say we have a copper conductor in a loop that goes all the way around in and out of the board this way. So as you rotate the magnet, and these lines of magnetic flux cut the magnetic or the electric loop, the copper loop here, it's going to induce current flow in and out of the loop, in and out of the board here. So everyone knows that already. So the point I'm trying to make though is if you rotate this magnet at some fraction of the speed of light, like say half the speed of light, the ends of the poles are flipping around. As you get further out from the ends of the magnet, these magnetic field lines are not moving faster and faster around this way. If that magnet is just one electron's magnetic dipole moving around, let's say it's going this way, then 100,000 miles out in this direction, you don't have some magnetic field zipping around at super high speed because its lever point's way down here and this way up here. It's not going to move like that. It's going to be more like visualize you got a garden hose, you're watering some plants and you move your hose over here. Well, that stream of water doesn't move with your hose. It keeps going straight out. And now it's going to start going straight out from your new position. So that's the way magnetic fields work too. You can't make a magnetic field speed up by moving a magnet this way. The flux lines don't move around with them. They always either go out where they used to go, or they start going out from their new position as you rotate the source of the magnetic field this way. Everything's always going straight out. Nothing out in space, not even a hundredth of an inch away from your magnet, is going to move this way with your magnet. They're always going straight out. So you can only change the new position where it's going straight out from. So in fact, this whole idea of magnetic flux lines cutting across a conductor is not really the most accurate way to visualize what it is that causes the current flow. You're not cutting across the conductor, you're just no longer making as much magnetic flux on one side, and now making more magnetic flux come out on the other side. And by doing that, you induce current flow in your conductor. So just keep that in mind for visualization's sake. We're never talking about magnetic fields out in space sweeping faster the further out in space you are from the source of a rotating magnetic field. Okay, next point I want to talk about, when we, in the world of RF, if you have a magnetic loop antenna, just a quick review of how they work, for ham radio operators like myself, who use magnetic loop antennas, you usually make them with a loop circumference just a fraction of a wavelength of whatever frequency you're trying to transmit. So for example, this total circumference could be less than a quarter of a quarter wavelength or less. Usually to make them with the highest efficiency, we try to make them between an eighth of a wavelength and a fourth of a wavelength. Just for the sake of simplicity, let's assume for this example right here, I'm making this circumference 1/10 of your wavelength of whatever frequency, and this is a capacitor. So what will happen is we'll couple to this loop with a smaller loop. This will run off to an RF generator. So we'll stimulate the big loop with a smaller loop, and the signal will oscillate back and forth. You'll build up electric charge on your capacitor, and when it's maximum, you have zero current flow through the loop. And when your charge reduces to zero, then you have maximum current through the loop. And it builds up maximum charge the other way. Hope I just flipped that correctly. I can't remember what I just had drawn there. But anyway, the current's oscillating back and forth through that loop, charging the capacitor one way or the other. And that radiates RF out into space. So traditionally, anyone familiar with transmitting with magnetic loops, you know your magnetic field builds up like this, and what you pick up from the loop, you don't pick up with another antenna. in this direction or this direction. What you really pick up the most signal from is the radiation going out this way and this way. And what you receive is really just the difference of the magnetic field radiating out from this before what radiates out from this the other way catches up with it. I mean, it just kind of depends on the diameter of the loop. So way out in the far field, you get a magnetic field going this way or this way and radiating out that way. And if you make a diagram of how the antenna's pattern looks, it looks kind of like you'll get the maximum RF radiation in this direction, in this way, and this way are called the null directions. You have another antenna out here, you don't receive anything. And the reason you don't receive anything is the magnetic field in this direction is facing to or from the direction of propagation. It's propagating this way, it's propagating that way in space, and the magnetic field is facing the same way, it's in line. So hopefully you can understand that can't cross a conductor. You can only cross a conductor when it's radiating out this way, but it's oriented this way or this way, then it's going to cross conductors and cause current flow in them. So, for example, if I have an antenna that's facing into the board, and this magnetic field propagates across it, so my magnetic field is going this way, it's going to induce current flow back and forth this way in my antenna, and that's how I pick it up. So this way, the magnetic field is propagating in this direction, but it's also oriented in that direction or opposite that direction, and so it can't induce any current flow. And per Maxwell's equations, all the people that design magnetic loop antennas tell you, well, you're not getting any energy radiated this way because obviously you can see there's nothing there to pick up. Your antenna doesn't pick it up. And one RF engineer, pretty smart guy that everyone has been giving a whole lot of flack, he's saying, his name is Mike Underhill, and back in 2003, I believe he published a paper that started him getting all of his flack, and he said magnetic loop antennas radiate a lot more energy than these people that go by the equations are saying, so the equations must be wrong. And everyone's telling him that they're proven equations, everyone goes by them, you can get out there in the field with another antenna or field strength meter and everything, and you can verify your equations are correct. What Mike Underhill was doing, he took his magnetic loop antenna and his coupling coil and ran it to his transmitter, and in line he put what ham radio operators like me always put in line. You put in a box that's going to tell you what your standing wave ratio is and what your power level. Alright, my camera just cut out. Hopefully we'll be going without more interruption. So he starts off seeing the same kind of readings that all other ham operators see, you know, when they start off and they say everything goes by the equations. But what he did was he started to precisely measure exactly how much AC power from his power cord. Actually, he probably has a AC to DC power supply. He's like most of us. So he spent years making precise measurements of exactly how much power, and he's no dummy, he knows you have to measure the phase of your voltage and your current coming in here to see the real power you're using. Once you've converted it to DC through a power supply, it's a little bit easier to make all kinds of measurements about exactly how much voltage and current you're coming in. And then the main thing he did was spend a whole lot of time taking thermal readings and measuring precisely how much heat is being dissipated by the power supply, the transmitter, this coax line, and the antenna itself. And after years of doing this, he tries to convince everyone, hey, I'm getting sometimes up to 1,000 times more energy radiated than Maxwell's equations say can be radiated. And that's because everyone else in ham radio was measuring what gets radiated as transverse electromagnetic waves. And although Mike Underhill never, as best I can tell, never looked into where all that energy is going, it's my contention that what he has ended up doing is proving that there is, in fact, from any source of a changing magnetic field, if you get current flowing this way and then that way, you'll get your transverse electromagnetic wave radiated out in these directions. But in the so-called null direction, you will get magnetic waves going this way also. And same this way. You'll propagate magnetic waves in the null direction, and they cannot be picked up with a dipole or any other kind of normal antenna, but what they do have the ability to do is pull on magnetic dipoles out in space away from this antenna and cause them to rotate into alignment or not. So he has inadvertently, with his research, shown, as far as I'm concerned, that there really is energy being radiated in these directions. So the reason I mention all this is we're going to apply that same thinking to rotating magnetic fields from precessing electrons. Even though maybe they're not easy to see per Maxwell's equations, there is energy being radiated in those directions, in as much as those magnetic waves, which do not induce current flow, still have energy in them, in as much as they can pull on the rotational orientations of other magnetic fields out in space. Okay, hopefully you got all that. In talking about Maxwell's equations, I just should review for a minute that the four famous equations we nowadays call Maxwell's equations are kind of a very pasteurized version of Maxwell's equations. That he originally wrote his equations in vector math called quaternions, and he had a lot of them, not just four. And later, Gibbs and Heaviside, who were into more modern day vector math, not quaternions, they converted his quaternion mathematics to the vector math that we use nowadays. And they did that by taking a subset of his quaternions. They did not use all of his equations. They just took part of his equations and then they converted those to the vector math equations that we use today and condensed them down to just 4 equations. So it's my contention that we may need to go back and use quaternion math or something similar to represent the whole of all the electromagnetic phenomena that occurs in the real world. That we're leaving off things like how to represent the magnetic force being pulled, pushing and pulling on other magnetic dipoles out in space in these null directions. And we are also ignoring the possibility of gravity waves like I discussed earlier, where the electric field components have been canceled out and all you have is alternating magnetic waves. We can't easily see that because we've factored out the math that we could otherwise have used to represent that.
Okay, so now I'll just give a quick and dirty simplified explanation how alternating sets of magnetic fields pointing in the same direction that they're propagating through space can create the effect that we know of as gravity. So if you have a group of atoms, whether it's the Earth or just a dust ball in space or whatever, all the atoms that make it up will have electrons precessing, most of them paired up in various orbitals. And as they precess and counter-precess, per discussions earlier, they will radiate pairs of magnetic waves. Twice per precessional revolution and counter-revolution, they'll radiate dual norths and dual souths. And in between, they'll create EMFs in current loops, which within the atoms can create counter EMFs by the orbital motions and interactions with the nucleus. However, the purely magnetic components that exist twice per cycle and radiates out in the same direction as the magnetic field vectors pointing, that doesn't get canceled out. So it continues to radiate out. If we presume a worst case scenario where all the precessing pairs and all the orbitals of all the atoms of a particular mass are in any random orientation, then we can divide that randomness into 2 basic categories, and that is that vector portion of their, if this is one example of just one of all the precessing and counter-precessing sets of paired electrons, and at this snapshot in time, both norths, the vector portion of each that is precessing around is up and up in this instant in time. 180 degrees precessional motion later, they will be down and down and radiate out in that direction like that. And the south of this likewise precessing this direction, and then alternatively switching to north, propagating in this direction also. So now, if we presume that of all the orbitals, all the precessing paired electrons in all orbitals of all the atoms that make up a body of mass are free to be in any random orientation, then a vector portion of, statistical portion of that will be pointing straight out from the center of the mass, propagating in this direction. And then there will be another vector portion of these
that will be in some angle within the plane around this way, at any arbitrary distance towards the center of mass. Any of them will have some of the random portion of them will be in any orientation around this way, sending out magnetic fields that alternate back and forth in the direction that they propagate. So that vector portion facing in any direction this way is going to radiate alternating magnetic fields that will push on and pull on the magnetic fields of all other precessing pairs, and to the extent that they have a tendency to move into alignment, then that portion facing this direction anywhere within the sphere at any depth will behave similar to taking a group of bar magnets and those bar magnets will tend to align north-south, north-south, and to the extent that they move into alignment, even at the same time that they may have spin waves propagating through them due to not having perfect alignment, to anyway, they would still have, to the extent that they are in alignment, they will tend to pull together with magnetic attraction here through between them. And in all layers going into the sphere, to the extent that some portion of those precessing pairs are having alignment in that direction, then they will tend to pull together this way towards the center, shrinking the whole accumulation of them. And then there will be another vector portion of all precessing pairs within all of these that, if not facing this way or this way at any level within the sphere, there'll be another vector portion of them facing in and out. And to that extent that they line up that way, they can be represented as like a group of magnets, even though these will be flipping end over end. Actually, each one of these is representative of two sets of scissoring magnets, and the signals radiated between them make them flip in synchronization, and so they'll tend to pull together the same as static non-flipping magnets. And the same occurs with that vector portion of the total mass that is flipping like scissoring magnets pointing this way. They will radiate this direction and this in towards the center, and then out of the center out towards this direction, or actually in all directions. They will tend to radiate in and out of the center magnetic waves like this, going in and out of the center. And so then again, the magnetic attraction will pull them together that way and pull them together towards the center from all directions around the sphere. So either this way and or this way, the tendency is for them to all pull together to the extent that they have a natural tendency to become synchronized due to the alternating magnetic field directions that flip back and forth twice per precessional cycle of all the paired electrons within all the atoms of that mass. So that's a very simplified way of trying to understand where the gravitational force comes from.